Stan Gibilisco here. A viewer asked me a very interesting question recently, and the answer is rather complicated. Uh, so I'm just going to give you an example of something kind of paradoxical about phase shift and inductance resistance or capacitance resistance circuits. As you may know, if you connect a resistor in series with an inductor and then send a signal at a certain frequency through that circuit, you will get a phase shift. That is, the current will lag the voltage by a certain amount of phase, which we symbolize by the lowercase Greek letter phi. And the value of that phase shift phi is equal to the arctangent of the inductive reactance divided by the resistance, the arctangent of the quantity of the inductive reactance divided by the resistance. Well, now let's suppose, just for the sake of supposition, to make things as simple as we can in this example, that we have a certain frequency, and we can call that frequency whatever we want. I guess we might as well just use the lowercase letter f. But whatever that frequency is, in this particular case, the inductive reactance is equal to the resistance. Let's just suppose that at a certain frequency we have a coil and a capacitor in series such that the inductive reactance is equal to the resistance in terms of ohms. It might be any number of ohms. It really doesn't matter. All that matters is that R equals X sub L, so that when you divide X sub L by R, you get 1. X sub L equals R. Now the arctangent of 1 just so happens to be 45 degrees. Let's just do a little example here. 45 degrees. Let's see what happens when we take the tangent of that. We get 1. So the arctangent of 1, that is the inverse tangent of 1, is 45 degrees. Just to double check to be sure that I was correct in my supposition. Again, this can be any number of ohms. So this circuit, when you send a signal at frequency f through it, produces a phase shift of 45 degrees. That is 1/8 of a cycle for those of you who care about that sort of thing. Now, my viewer's question was, suppose that you connect two circuits just like this. Two circuits just like this. Well, I'm using the wrong. I wanted to use, well, let's just forget about that. And consider that we have a circuit like this that produces a 45 degree lag in the current with respect to the voltage. And then we take another circuit just exactly like it. Same inductive reactance, same resistance, same 45 degree phase shift. If we send that signal through this circuit, we get a phase shift of 45 degrees. If we send that signal through this circuit, we also get a phase shift of 45 degrees because the circuits are identical. Now, suppose that we take these two circuits that produce this 45 degree phase shift and we connect them in series with each other. And I'll make it so that we have the resistor coming first, then the inductive reactance, the inductor, then another resistor, and then another inductor. And we consider this as a single circuit. Now we send the signal through this whole circuit. 45-degree phase shift if we send it through this circuit alone. 45-degree phase shift if we sent it through this circuit alone. Now, doesn't that imply that we're going to get a 90-degree phase shift here with respect to here, that here the current is going to lag the voltage by 45 degrees, and then here it's going to add another 45 degrees, so that here we find that the current lags the voltage by 90 degrees? It only makes sense, right? It seems to make intuitive sense. But the fact is that phase shifts do not add simply like that. Because, remember, resistances in series add directly together. Inductive reactances in series also add directly together. So what we're really going to end up with here is 2 times the inductive reactance divided by 2 times the resistance. And we're going to take the arctangent of that. The phase shift is going to be the arctangent of that. Remember now, R and XL were equal, so 2R and 2XL will also be equal. So we're going to have the arctangent of 1, and that, as we have already seen, equals 45 degrees. So, if we have one circuit that produces a phase shift of 45 degrees, and at the same frequency we take the identical circuit, which by itself would produce a phase shift of 45 degrees, and if we connect those two circuits in series, we're going to end up with the exact same phase shift that we had with either circuit alone. Phase shifts do not simply add as resistances or inductive reactances do at a specific frequency. They don't add because the arctangent function is a nonlinear function. I don't know if I've made that terribly clear by only one example, but his assumption was that we could add these circuits in series indefinitely, or his supposition appeared to be that we could add these circuits to each other one after another indefinitely and get 45 degrees, then 90 degrees, then 135, and then 180, and then 225 degree phase shift, and that the current would just lag the voltage by more and more and more. But in fact, if we take circuits like this where the resistance and the inductive reactance are the same, and we add them one after another in series, we're just going to keep getting a 45 degree phase shift at that frequency. It's as if we add up an indefinite number of numbers and always end up with the same sum. We're not getting simple addition here with phase shifts as we do with inductive reactances or resistances. So keep in mind that when you want to find out the phase shift produced by a complex resistance reactance circuit, you can't just add up the phase shifts and expect to get the resulting phase shift correctly. You have to find the net inductive reactance or capacitive reactance and the net resistance of the whole circuit, and then take the arctangent of that ratio to get the phase shift that you will end up with when you send a signal through the entire circuit. Phase shifts do not add like regular numbers do. That's why I said it was a complicated scenario, and I've seen scenarios, or he told me that he has not seen scenarios like this outlined in ordinary textbooks, that they seem to gloss over this subject or this approach to the matter. And I told him the reason is because it's complicated. And he came back and said, I can't imagine how it could be complicated. Well, perhaps now you can begin to imagine why it's complicated. I invite you to create a variety of problems like this as examples for yourself. Use my book, Teach Yourself Electricity and Electronics, in which this formula appears both for capacitive reactances and resistances, and goes into considerable depth as to how to derive this phase angle. But it doesn't get into complicated circuits like the one in which the stray green line appears, which I shall leave for emphasis. 45 degrees plus 45 degrees equals 45 degrees. Such is life in the complicated world of phase shift addition. Once again, my book, Teach Yourself Electricity and Electronics. I recommend the paperback version of the 6th edition, available from Amazon.com. You can get it used if you want it cheap, or you can maybe find it in your local public library. Happy complexities! Enjoy these sorts of addition, because you aren't going to come across a situation every day where you can add something to itself and get itself all over again. Stan Gibilisco, signing off. Until next time, so long.